Hello, I'm starting the live stream. Here we go. um, the plan today is that we talk about the same problem as last week. If you're joining us for the first time, this is Chill Maths on Twitch. We do maths problems, but not very quickly. Right, yeah, I did it right this time. There we go. Right, okay. We'll trim off the first 3 minutes and no one will know. That'll be fine. Highly professional Twitch stream over here. We unmute all the time. Right, what are we doing? We've got... Hello, good morning. Yeah. So we have some patterns. Let's recap last week for people who are joining. Maybe you've clicked on the recording without watching last week, which is... Yes. This is the internet. You could access this content in any order. Here we go. Maybe you've seen next week's video before this one, in which case let us know in chat what the answer is. So we're choosing 12 integers from 1 to 100. I might refer to these as cards because the original version of this problem has these as drawing cards from a deck, but I don't really want to think about card games too much, but I might say cards just for, just to mix it up. We had a strategy that works. It's a big recursion relation to think about as you've either picked the number 1 or you haven't, and then if you've picked the number 1, it's part of some string of consecutive numbers, maybe just the number itself. And in those different cases, you either have already made your set of 4 consecutive numbers that we're looking for. There they are, 4 consecutive numbers that we're looking for. If you've got 1, 2, 3, 4, or much more likely you have failed, maybe using up some of the cards that you drew from the deck. Some of the numbers have already been used if you picked like 1, 2, 3. So it might be quite bad news. You wasted some of the numbers, and now if you're going to make this happen, you have to draw 4 consecutive numbers from the remaining numbers. But in either case, whether you failed without having any numbers here or failed with some numbers here, you now have to succeed with the remainder of the numbers. So we thought about those as kind of separate cases. Here they are. If it's not chosen, then you got this. Hello Neutrino, hello Mary, hello Mountain Ash. Else you might pick this. Actually, we were thinking about N, thinking about the other end, I remember now. There was this kind of exceptional case where you had 4 in a row right at the end of your numbers. You pick the 4 largest numbers out of the hat, in which case nothing else matters. You might have picked the other ones, or not. Good, which means there's actually quite a lot. That one's quite nice because if you pull that off, if you pick those 4 largest numbers, then it doesn't matter which of the remaining n-4 you pick. So we're thinking about the kind of general problem here where you have numbers 1 to n, and you have to pick k of them looking for a set of 4 consecutive numbers. If you bring in those n and k variables, then you can start to relate together different versions of this problem. Something like, I did have the number 100 but not 99, so if there's a set of 4 consecutive numbers, in this case, I would need to pull out of 11 numbers remaining to be chosen from 1 to 98. Still need to find my 4 consecutive numbers. So it's kind of this term here. This relating to the idea that you might pick 100 but not 99, and then, oh no, you've got to do this using k-1 picks. So we have this kind of recursion relation that says the function value is equal to other values of the function using smaller inputs, which actually build cumulatively. So we wrote some pretty bad MATLAB code, to do that, which looks like this. There's some small cases that we solved as well to do with if you pick all of the cards, then you might get 4 in a row if you were picking 4 or more. So there's some small cases that we did, and there's some recursion here to say fnk is equal to the sum of these previous things. And if you write to a matrix in the correct order, you can build up this thing. That's what we did. Then we looked at the numbers, and we found out that, well, here they are. They're very small on the screen, aren't they? Can I make that larger? I don't know how to make that larger, sorry. No, I've no idea, sorry. We noticed, I'll read it out, that these look like the counting numbers, these look like the square numbers, and then we looked up this sequence on the online Encyclopedia of Integer Sequences, and we found out that's something nice as well. We also think that's something nice on OEIS. So we looked up these sequences, and the point we got to, I sort of messed up writing this down, but the point we got to was to say it looks like maybe this is, I've written this completely wrong over here, so I'm going to tidy it up a bit. Yeah, I was running out of time and I wrote poorly. n minus 4, choose k minus 4. So fixing this, I went and fixed it. There's some sequence here which matches, in some sense, if this is choosing 1, if it's 1 down here when k is 5, then you get the numbers multiplied by something else that looks like n. There's this kind of shift here because of the diagonal going down, but whatever. This took me a while to piece together, but so this would then agree with this formula up here, n minus 4 squared when k is 5, because this choosy thing would say you're choosing 1. We know what that is. n minus 4 choose 1 is just n minus 4, and this term here would also be n minus 4. So I've got this question now: is it this? To which the answer is sadly no. This is the cliffhanger we left the stream on last week. So the answer to why is no, which is doesn't quite make sense, but close. It does. It stops working at n equals 8, and it is interesting to think about why it stops working when n is 8. So the why question gets replaced with this larger sort of why and why not question. Like, why does it work to start off with? This works for case 4, 5, 6, and 7, but fails when, sorry, it works when n is 4, 5, 6, and 7, but fails when n is 9. Fails when n is 8. I will get there. Chill maths. It stops working when n is 8. Just read chat. If in doubt, don't listen to me. Read chat. Right. Elle's popping by. Hello, maths is chill. I think in between streams, I've solved a problem. I'm going to try and explain how I solved it, as well as what the answer is. We've got something that works well for most of the cases here, but breaks down when we get to 8, which says if you have, oh no, this is k. This is k along here, isn't it? Because we're good for large values of n. Yeah. Which way around does it break? I think this is true. For the large n is fine, but it breaks when, I can't remember which way around my table is, it breaks when k is 8. So, yes, here's my claim. Yes for k is 4, 5, 6, and 7. Not quite. For k equals 8. It is n. Everyone's telling me it's n. Right, hang on. I think I've coded this up so that my function is f of nk like this. It has 100 rows. There they are. And only 12 columns. So I think this way is how many cards you're picking. This way is how many cards you're picking. And we run into trouble if you're picking lots of cards. But this down here, reading down the column, these genuinely are different square numbers. This is n minus 4 squared as a function of n. So as you change n down here, when n is 23 or something, nothing goes wrong, it's n minus 4 squared. So large n, I feel like we understand, which I can make sense of in a second. Yeah, this table, so this table doesn't give the right answers if k is greater than or equal to 8. It says lazy shooter 101, and I agree with lazy shooter, I think. And they've done some simulation. We can also do some calculation in here. So I've got a pretty simple formula down here to just do that choose function so that we can compare. So if I calculate this, then I'll get g as well. G is kind of my comparison. It's not the function f, it's the next letter of the alphabet to do n minus k plus 1. Choose this. Relate to k minus 4. What do you mean k minus 4 is 0 until k equals 8? Yeah, that doesn't make sense to me, sorry. I think if k is 7, then k minus 4 is 3, which I'm happy with. Okay, I might be missing some of the numbers in that. Anyway, you can calculate this and compare. If you do, then I get this second matrix, G, so I'll scroll back up again. G, which kind of agrees in, I don't know if you can see, it agrees in the first 7 columns, but then disagrees in column 8, just here. It's 9 or 10. And it's those columns onwards where it breaks down. But those first 7 columns are just fine. I mean, there's loads of zeros over here, so not much to write home about. But then those next columns are fine. This is just experimentally looking at the numbers. There's a choose part. Yeah, so my choose part here says something like, for example, k equals 7. I think that this minus 7 plus 1 is 6. N minus 6, n minus 4, choose 3. I think this is correct for all n. And this n minus 4 choose 3 thing is something mildly complicated. N minus 4, n minus 5, n minus 6 over 6. And which is a bit of a mess. It was also multiplied out by this n minus 6 at the front. But this sequence gives me, starting with n equals, well, starting with n equals 7, this gives me, well, not very much, right? But starting with n equals, for n equals 8, this does give me the correct value, I think, which is, let's put a 7 in here if k is 7. If n is 8, this gives me, e.g. f of 8, 7 is 2 times 4 times 3 times 2 over 6, which is 8, which, do I believe this? If you have 8 cards and you choose 7 of them, there really are 8 ways that you can get 4 in a row. I think. Do I believe that? 8, 7? Oh no, if I've made a stupid error there. Yeah, okay, there's an 8 in this block, 8 in this box. Let's see if I can build that up. If you've got 8 numbers, 3, 4. I should be able to do this, right? 8 is a small number. Yeah, and then whichever one you don't pick, you will end up with 4 in a row on the left or on the right. So this is all of them. Maybe a more exciting one. Oh, the first part of the recursion relation. No, hang on. So my recursion relation involves an n minus 4 choose k minus 4, I think. Where's my recursion relation gone? Up here. Here it is. I'll put a pink box around it so I can find it faster. Ooh. Fine. I'll do it like this. Chill maths. Also involves working with my whiteboard as best as I can. There we go. Purple box. Thicker box. Nice. Subtle. So not much goes wrong. If n is 100 and k is 7, then all these terms check out. It's a complicated sum to do. But I claim that it turns out that when n is 7, so when k is 7, rats. When k is 7, you always get this expression, which is a polynomial of degree 4. How do I know this? Where's this come from? I've got a reason for this formula, which again only holds up to 7, but then I've got a fix for it based on the new understanding that we get from thinking about where this formula comes from. Here's a kind of key idea. So I'm going to bring this down here. Key idea, if k is less than 8, so if k is less than 8, then removing 4 consecutive numbers, I need to be specific, removing the first 4 consecutive numbers from the, I'm going to justify that in a second, from the block of 4 or more consecutive numbers, leaves no blocks of 4 or more consecutive numbers. If k is less than 8, then you don't run into this position of having two separate large blocks, which was a problem for our counting method last week. We had this counting method last week where we would talk about the block of 4 consecutive numbers and run into this problem that it might not be unique. There might be some overcounting due to these having two places where this block of 4 might occur. I've put the words the first 4 in there because even with k less than 8, you could have 5 in a row, which also confused us last week because we had this counting method where, unfortunately, our counting method would identify the first 4 and the last 4 as kind of two separate occurrences of 4 in a row, which I don't really want. Oh, I've gone slightly off screen there. Why has that happened? Because this is not the right size. There we go. Okay, so for these problems, you can do 2 steps. If k is less than 8. Here's what you can do. You can permute. So permute, what do I want to permute? K minus 4 chosen items and n minus 4 not chosen items. So these are the kind of diagrams we've been drawing where you circle the numbers that you're picking or something. You end up with this pattern where you picked some of the numbers and you didn't pick quite a lot of numbers. If n is large, then you are not picking lots and lots of numbers. But if k is quite small, then there's not very many of these ones that we're picking. Especially if I'm thinking about permuting k minus 4, there's only at most 3 of them. Here's the good bit. So that's some permuting that we can do to shuffle around. Okay, there's going to be some that you don't pick, some that you do pick. Here's the good bit. We could then choose one kind of string of consecutive chosen numbers between 2, maybe not between 2, but one string of consecutive numbers, possibly no numbers, and add 4 chosen items to that set. I'm mixing language quite a lot. I haven't quite worked out the language for this. What I'm imagining is there's only one place where there's 4 in a row. If k is less than 8, there's only one place where we get 4 in a row. Can't have 2 because that would involve 8 things. And if they overlap, that's one big string, which is what I mean. There's only one string of 4 or more consecutive numbers. So if you remove 4 from that, you have no strings of 4 consecutive numbers because that one is not large. That one is now too small because you remove 4 from it, and k is less than 8. So it was at most 7 in length. You remove 4 from it, and now it's short. Even if these 3 remaining things are in a row, that's not 4 in a row. So think about shuffling that, and then put the 4 back in. The bijection here is between permutations of these and choose which of these kind of positions. Let's mark in the positions which I could play a kind of +4 card on. It's these places where there's a string of usually 0, sometimes 1 or 2 or 3 chosen items in a row. I have this kind of add 4 card. Bam, which you can play in one of those locations. In one of those locations to add 4, 1, 2, 3, 4, add 4 of these in one of those locations. And because I'm adding it to the start, I'm thinking about either removing the first 4 of the consecutive numbers or adding back in the first 4 consecutive numbers. Because I'm thinking about putting it at the start, I don't get overcounting from a large string of consecutive numbers. There's only even 6 things in a row. There's only one way to remove the first 4. Which is then leaving me thinking about permuting just a couple of things around. Or maybe they've ended up like together, and then I hit it with the +4 to bring it up to 6. I'm mirrored, aren't I? This is the front. So in this way, you can very carefully build each sequence, each kind of sequence of circles and crosses that has exactly one point where there are at least 4 in a row. By thinking about where that point is relative to the ones that you're not picking, the kind of different strings of consecutive numbers that you get. Think about where that is, and think about what was going on with those other 3. So this fix works for k less than 8. I'm relying on that quite a bit. And then there's a slight fix that I can do. This way of thinking is good because I can go beyond k equals 7 with this way of thinking. So I wanted to show you this first before I do the kind of madness of. I'm going to think about what would happen if you added 4 in. With k larger than 7, you might have some overcounting due to playing the +4 card versus just shuffling and having 4 in a row. Let's do an example. Maybe we should do the 8,7 example. 8,7. Let's do the n-4 squared example. Because the number of pink arrows, just to finish it off, the number of pink arrows, number of places to do that. I'm going to say play the +4 move or card or whatever is, and then it's it's not quite n because I'm only looking at the ones that you don't pick, which is n-k, the ones that you don't pick, but then +1 because n-k is how many x's there are. And then the +1 is because you could go right at the end after. You can go to the left. It's fence posts. The fence posts kind of split up any consecutive strings you might be getting. Most of the consecutive strings are 0 length, which makes them hard to see. Like there are no circles here. Still a good place where you could put 4 circles in a row. Let's do an example. 5 is less than 8. So here's my way of thinking. First off, you permute lots of x's, n-4 of them, and 1 circle. n-4 of these. There's lots of ways to do that. You can imagine all of them, I think. There are n-5, choose 1 or something. n-k, sorry. Yeah, the number of ways to permute all the things you're not choosing, which is n-k, and this 1 circle. Permute these, so e.g. you will end up with 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. This. Now add to some string of O's, possibly 0 length. I kind of want to say between 2 x's, but there's those ones on the ends, so let's hope that's not too confusing. Or at front or end or something. There we go. So there's lots of places you can put that. You can put it at the front and then type out this 4, 5, 6. You can add it into this string here and then get the rest of these x's. Or you can leave that one alone and boost the next gap. 1, 2, 3, 4, 5. Or you keep going to get something like this. I've got lazy. and then 1 at the end. 1, 2, 3, 4, 5, 6, 7. Oh, and I've forgotten the one where you go right at the end and you boost. 4. Cool. Okay, so there's lots of possibilities about where you put in those 4. But as you do that, you have choices about where to put this 4. It's not, and we had this problem before, it's not every gap in the sequence here, left of the X, right of the X, and then here, or the here and here and here and here. It's not every gap, because putting it before this O and after this O would give the same sequence. So when you see some O's in a row, you don't go along saying, it could be at the front, or it could be in the middle, or it could be the end. No. You're supposed to just count how many strings there are, which means counting the X's, not the O's. To put 4 kind of O's at the front here, or here, or here. To skip over to say, I'm just going to count how many X's there are. So the number of choices here of where to put this block, no matter the permutation, the number of choices of where to put this block is the number of X's plus 1. So n minus 5 plus 1 choices for where to put the block of 4. Last week we would have accidentally said one more than that for this picture. We'd have said, because you could put it here or you could put it there. This is the fix, to say no. Don't count the places to put it in this sequence of symbols. Only count the different strings of zeros that you've got, which are defined by being in between 2 X's, or at the very left or at the very right. Right, so you have 2 choices, you make those independently. Here's why it's squares. There are n minus 4 ways to do this first bit. Oh, that's a terrible colour. There are n minus 4 ways to do this first bit, to permute these things around, and there are n minus 4 ways to add in the block of 4 zeros, if you're very careful about where you put it. Last week we would have said n minus 3 by mistake. You make those independently and you get squares. But that's the thing that this is the I think right way to think about it. That you're putting in this block of 4, but you're being careful to put it at the start of a sequence of zeros. You could say that you're always putting it at the end, which is why the mirror reflection on the screen doesn't totally matter, as long as you're consistent and don't count both. We're putting these 4 circles at the start of each block of zeros. Luckily, we can still count those because we know that blocks of zeros occur between 2 X's, or at the very front or at the very end. That's my counting innovation. Right. So this works even if you have, even if you have 2 or 3 circles in up here, for a kind of k minus 4 kind of situation up here. How many of these have we got? K minus 4. This is. I need to label this as well. It's 1 in my picture because n is 5. I'm going to label it as k minus 5. K minus 4, sorry, which is 1. Yeah, so for k equals 8, you can have blocks of 4 before the plus 4 comes along. So you will double count, but you will double count in a very particular way. So this is a formula that works for k up to 7, which you might have found. It's an explanation for why it squares, because you're separately shuffling. You're not. Yeah. Okay, you can imagine these as fence posts for both, right? That's a different way of thinking. No, I don't love it. Don't love it at all. You shuffle these around because any extra circles you've got are indistinguishable. So you shuffle those around and then you put in this plus 4 in one of the slots. Here's the double counting and how to fix it. We're now going to go from k equals 8, 9, 10, 11. And the actual question is to do k equals 12. So we're one step away from that, but we're getting there. So here's how to allow for this. Here's the problem. I want to do the same thing exactly. I want to take n minus k, things that I'm not choosing, and k minus 4 things that I'm choosing before I do the +4 bonus, but there's going to be a double counting. There's going to be some double counting, and the double counting is not hard to count, so we're almost good, I think. Once I show you one more thing, but I'm really pleased with this. Which was a really hard problem that I feel like we've come up with 3 different ways of thinking about it. One of them didn't work, and 2 of them maybe have. Yeah, we're gonna think about what doing the +4 move twice would be like. Yeah, so we sometimes get, and here's the kind of generic picture of what I don't want. A bunch of x's, cool. And I guess this is k equals 10 or something, just to prove a point. But we sometimes get these 2 different bits that might have been made by, adding 4 to something. It's no longer true that if we remove 4 from the front of the sequence with 4 or more, that we're left with some simple permutation thing. We've double counted. If there are 2 strings of, I need a better word for this, strings of 4 or more consecutive, I'm writing it terribly, integers. If you've got a good idea for what we could call these, but then it's tricky, isn't it? Because we all have to agree what the word is. Yeah, we're going to get rid of this double counting. How many ways are there to do that? And this is a concrete problem. And to be clear, we've double counted them. Because we might have played our +4 card here, or we might have played our pick up 4 card over here. There are 2 strings of 4 or more. 2 strings of 4 or more, so there's only 2 places we might have played our +4 card. There aren't 3 strings of 4 or more, because k isn't as large as 12. That's going to come back to bite me in a second when I want to talk about k equals 12. But there's maybe 2 places where we overcounted. So we can get rid of the double counting using the +4 move twice. Here's what I want to do. Consider permuting. Hi, E is better than pi. How are you doing? My handwriting just went through a little spike of being even worse than normal, so I'm going to rewrite that. Maybe I should be typing. No, boring. You didn't come here to see me type. We're doing a counting problem. I'll tell you in a second. We're doing the big reveal, I think. People are maybe ahead of me in chat. Let's find out. I'll tell them, they can think about it, and then I'll tell you the problem. We're going to consider permuting all of the kind of nonsense things that we're not picking, and k minus 8 of the things that we are picking. Then use +4 card to 2 distinct strings. So find 2 places to play your +4 card. This is a way to count how many of these things there are where, slight problem, we've had 2 long strings. Hello, E is better than pi. Here's the problem. Oh gosh, we've written quite a lot of stuff today. Most of this last week, actually. A student on a summer school gave me this problem, so now I'm giving it to you. They chose 12 distinct integers from 1 to 100 inclusive, and they're interested in the number of ways you can do that so that you get 4 consecutive integers. Oh, it's you. That were you. Oh, hello. Welcome to the show. We're pretty close to solving it, I think. How you doing? What a small world. Yeah, we're doing your problem. We talked about a way that doesn't work, but then we talked about a way that does work with recursion. We put it into MATLAB to calculate some numbers. We noticed once we put it in MATLAB, look at this. Once we put it in MATLAB, we noticed, oh no, we know these numbers. These are square numbers. We put them in sequences, and we found that there's a pattern for these first 4 cases. These columns are for k as 4, 5, 6, and 7. 4, 5, 6, and 7. The pattern breaks down for k equals 8, but thinking about those cases is how we got there. The key idea, I think, is that if you're not picking very many cards, then you can imagine that the string of 4 or more came from adding 4 to the front of a string of numbers, string of selection indicators. I've got this weird thing going on where I'm doing these crosses and circles because I'm thinking about I'm going to end up with my 100 symbols in a row. Either I've circled some of the cards that I'm picking or crossed for not picking these of the 100 numbers in a row. So all I need at the end is like a list of these permutations of circles and crosses such that there are 4 in a row or more, 4 or more in a row. If you're not picking very many cards, if you're in an early round of the card game Mind, then the only way that you could get 4 or more in a row, they all come from permutations of not many circles, but then one of them gets pumped up by adding 4 to the front. Yeah, here we go. People are now doing the k-8 thing. This is pretty good. It works for k less than 8. You imagine that you're permuting all of the crosses and k-4 selections, and then adding 4 selections to the start of a string. And the bad way of counting this, that gave us the wrong answer at the start of last week, the bad way of counting this is to say, well, I can put the 4 zeros here or here or here or here in between any of these symbols, but that overcounts because a string of 5 would arise from putting 4 circles before this one or 4 circles after that one. At the end of the day, once you select the cards, all the circles are the same as having 5 in a row. You don't want to overcount. The way you avoid overcounting is that you promise you will only put new circles at the start of a string, with strings being the things between 2 x's, or at the very start or at the very end. There is going to be a universal fix. It's going to be fine. It does depend on k, but we're going to go to infinity in a moment. Don't worry. I know it looks like I'm only doing 4 numbers at a time, but there's a pattern to the patterns. So we're going to take the big step. Okay, this works well up to n. This works well if you're choosing 7 or fewer cards, because I can say, well, your string of 4 in a row. If I remove the first 4 from that, then you're doing something with no strings of 4 in a row, just 3 things, and 3 things you're choosing. Goodness me, n minus k. Complex numbers later. Okay. If you're choosing 8, 9, 10, or 11 cards, here's what's true. You might have 2 strings that are 4 or more in length, but you don't have 3. So you might have done, with the above method, a little bit of double counting, but it's a very controlled amount of double counting because we're no longer... We've solved the problem of overcounting a string of 6 in a row, overcounting that by a factor of 3 because we were thinking about putting the 4 O's in between each of the gaps. If we promise to only ever add 4 zeros to the start of a string, then we fix that sort of overcounting. And the only sort of overcounting we need to fix for now is how many of these long strings do you have? If it's 2, then you've double counted that because you might have made this one naturally by permuting and then added 4 over here to make a second one that's a long string. Or you might have made this one naturally by permuting x's and o's and then added 4 in over here to make a second long string. Similarly, in a minute, for people interested in k equals 12 or more, if you have 3 long strings, you've triple counted. But that's fine. That's a plus or minus sort of term. Here we go. So to count the cases that we've double counted, the ones with 2 long strings, I'm going to imagine removing 8. Imagine removing 8 of the ones that you're picking and permuting the rest of this stuff. Same idea though. I'm going to add 4 to 2 strings, to 2 different strings, because I want to pump up 2 of them to be large strings. And the control here, the reason I'm only going up to 11 is to control it to make sure that there's exactly 2 that I get out at the end. And I'm choosing distinct strings so that I don't, in this bit, count any ones that just have a really long string. What does that look like? Well, that looks like the permutation bit looks like n-8 choose k-8, and then you multiply because you've got some choices about which of the n-k plus 1 terms do you pump with this plus 4, add 4 circles to the start of that string. That gives you exactly the cases where you double counted. It looks good as well, right? Like, here's the permuting the X's and O's, and then here's the bit where you choose where to play your plus 4 cards. The n-k plus 1 is the number of places where you can play a card, the number of strings either between 2 X's or at the very front or at the very end. And we're choosing 2 of them because we want to make 2 long strings. This fixes things up to 11. Let's have a look. So I've typed this in already, so I'm gonna uncomment this. My code here says something like, if n is large enough, and if k, crucially, if k is larger than 8, then subtract off. Subtracting because we double counted. Subtract off this much times that much. The original one in here, by the way, is that's like n-k plus 1 choose 1. So there's kind of a pattern here. n-k plus 1, n-k plus 1 choose 2. Okay. If you do that and run it again, then this should have updated G. So now I hope that these things agree in the first 11 columns, which looks pretty good. That's what we've got. Everything on screen at the moment is exactly the same, including this 2496 down here. You know, checking small cases isn't the same thing as knowing that you're correct, but we've got a good reason to think that this formula is good. And this is checking, several hundred cases on screen. Let's scroll down a little bit. Compare these numbers. Yeah, they all match up as well, don't they? No pixels are changing here. Pretty good. Problem though is that we really care about column 12, because when the student who's in chat gave me the problem, the number they had in it was 12. And 12 is 3 times 4. There is a tiny possibility when you choose 12 numbers from 100 that you get 3 long sequences of length 4 or more, which means that this number here, for example, is 13. That's all right. But then we're out by 1 here. There's 91, which is not good enough. We need to improve it. We need to improve the formula just a tiny bit. So it's last week we did a stream where we went through the method that doesn't work and the recursion formula, and right at the end we spotted some patterns. This one is the one where we're explaining where the patterns come from, carefully permuting. Yeah, 3 times the plus 4 thing. E is better than pi. And I guess general warning for anybody. There's a good chance if I meet you in real life and you give me an interesting problem, there is just a good chance that I mine that for content, either on here or somewhere else. This is increasing the number of people whose usernames I can now match to actual people, which is a bit scary. But hey, right, we're going to fix this. Let's go. Right, let's do this. Just put k equals 12. This is what you came for. Can I have the pen but not have the pen menu open? Is that a thing? I'm sure that used to be a thing. Never mind. Okay. Clear menu. here's the thing you came for when I'm done grumbling at my whiteboard. K equals 12. There's a small chance that you had 3 long strings. If a sequence, so let's think, if a sequence has 3, I'm calling them long strings, I think. I've been calling them long strings out loud, ones with 4 or more in a row. 3 long strings, then we counted it. We counted it 3 times in the n minus k plus 1, n minus 4, choose k minus 4 argument. That's pretty good. We counted it. We triple counted it because you can make that by adding 4 to the front of any one of these 3 long strings. We counted it 3 times, and then we've subtracted. Our formula at the moment is subtract this. Subtract this. It's overcounting, so we subtracted it. In MATLAB, I think you saw I had a minus sign. So we counted it. Now for k equals 12, if you've got 3 long strings, and this is actually going to work for this many numbers as well. We counted it 3 times in that first argument where I did with the +4 card. We counted it, and this is going to have a minus sign because we counted it -3 choose 2 times in the n minus 8 choose k minus 8 n minus k plus 1 choose 2 argument. Now I've written minus because we're subtracting in that one, and we've got 3 choose 2 because that was about choosing 2 places to play your +4 card, and if there's 3 long strings, then oh gosh, you've picked that up in loads of ways because you might have picked any 2 of those strings to be the ones where you played your +4 card. So altogether we've counted it no times. So we should count these and add them. We counted them 3 times, subtracted, oh gosh, 3 times, so we should add them back in once. Yeah, I'm only inserting, thanks Maths2 to do that. I think does answer the Lazy Tutor's question, which is my possibilities in this list. I've skipped from the case where you put the 4 circles left of this circle. I've skipped on to this next point because I'm only thinking about the positions, which at one point I marked with pink arrows, being points in between the x's, to make sure that I don't count that string twice. Aha, there we go, good. I've written all that out. This is something called inclusion-exclusion, I think. The formula is not bad. The formula we're going to get is that we should add on, generalizing this thing that we just wrote down. You should take the n minus 12, saving 3 for your 3 + 4 cards, but take n minus 12 symbols, where I guess k minus 12 of them should be circles. You have n minus 12 symbols, saving loads of circles for my 3 + 4 cards. n minus 12 symbols, of which k minus 12 should be circles. Shuffle those around, and now boost 3 of the slots, 3 of the positions, by playing a +4 card in 3 of those positions. That will give you 3 long strings, which we triple counted. We untriple counted them, so we should count them and add them back on. A small world emote would be nice, wouldn't it? If you discover that a live stream on Twitch is talking about a problem that you gave to the streamer. I've been crediting you. I've been saying a student on a summer school gave me this problem because I did not get permission from you in real life to tell people your name. So I've just been anonymously crediting you, which doesn't really work, does it? Never mind. Yeah, inclusion-y, exclusion-y sort of stuff. Our formula so far, by the way, looks like this. F of nk is equal to n choose 4, n minus 4 choose k minus 4 times n minus k plus 1 choose 1. That's the first thing that we wrote down. Then we decided to subtract n minus 8 k minus 8 to allow for overcounting. And then we decided to add for this triple counting. Should add these on exactly one time. We triple counted them, we untriple counted them, we should add. It's quite wide, there we go. Plus or minus signs, good, right. And then I think it just keeps going. I'm going to write plus dot dot dot, or maybe minus dot dot dot. Let's go minus dot. And that just keeps happening, I think. I'm relying a lot on this idea that it keeps doing alternating plus or minus signs, but on the other hand, I have now made it to 12. So we can now fix our code. If you accept this thing about choosing 3, I've got faster and faster through the argument each time, but hopefully we're getting there. To get down to 12, I can throw in this thing. E is better than pi, there's your number on screen, by the way. Run that again. And then hopefully this has fixed the numbers in the 12 column. Yeah, there we go. Now it says 91. So this is F, this is G, it says 91. I don't know how convincing this is really, but there's some cases with the correct numbers. The only mild problem we're going to have is that my computer goes into scientific notation. It does know the numbers though. They're not that big. So scrolling down a bit here, we get huge numbers, and they keep agreeing until I get down to 100. N is 100, K is 12, but more importantly perhaps, 1.1791 times 10 to the 13. Yeah, looks good. Let's try and access that. Oh, yeah, I did mean that. Sorry for the loud computer noise. This is slightly awkward. MATLAB is not very good at whole numbers, but it does luckily have just enough precision that this is our number before those zeros in there. Yeah, it's this. So that many ways. Which we sort of knew from our recursion relation, but now we've got an exact expression for it as well, which is that 100 choose 12, sorry, F112 is 96, I just need to copy this out, and 3 terms is enough. 96 choose 8 times, this is 89, and there's a lot of 89s in this. Choose 1 minus 88, choose 4 times, and this term here is still 89, choose 2, plus, and then 80, oh no, take away 12, so take off another 4. I don't mean 80, I can't subtract. 100, 100 take away 8 is 92, take away another 4 is 88, there's an 88, choose K minus 12, 0, 89, choose 3. No typing, yeah, he didn't see me. He didn't see me typing. Hang on. 7, 9, 0, 5, 4, 8, 6, 5, 6, 8, 4, 4, 1, 1, 7, 9, 0, 5, 4, 8, 6, 5, 6, 8, 4, 4. No typing. But more importantly, it's just this in terms of choosers. And then I don't need another term because these will go to 0 after this term. And in general, I think you keep doing plus and minus signs. That's something I'd like to explore, I think, just to make sure that it keeps going plus and minus signs. But I think it checks out. I think it's going to be binomial coefficients kind of thing. That yeah, I'm going to do a quick scribbly bit of calculation. I don't know how much sense this is going to make. I'm going to try and convince myself that it's plus or minus signs forever. You know, just minus, plus, minus, plus. In general, here we go. Yeah, there you go. Thanks, Lazy Tutor. That is a good question. I think we'll go. Oh, no, that used to. So to convince myself, if you've got K, not K, if you've got M long strings, then you choose1 count them when you have 1 plus 4 card. In that bit of argument, you double counted them this many and subtracted this many when you thought about using 2 plus 4 cards, and so on. So what's this going to be? -1 to the... You're going to keep counting this until you've so far considered using m-1 plus 4 cards, and you'll decide that there's a plus minus signs here. So far you've been doing plus minus signs, and you've just got to the term that's like correcting for, you've just remembered that you might have m long strings, like how we just corrected for having 3 long strings. You keep going until you get to m long strings. You've got lots of terms so far. You've got m-1 of them, and this number here is supposed to be something like, what is this then? So it's plus if the number downstairs is odd. So I'm going to write -1 to the m like this. Yeah. Yep, like this. There's -1 to the m in here that's making me a bit nervous, but that's okay. Good. So how many times have you counted them? This many times. And amazing realization, we can use the fact that for binomial coefficients, this is true. Do people know this fact? Maybe you know this fact. If you write out binomial coefficients in the mth row, in any row, this is 1. If you put a minus, then a plus, then a minus, then a plus, and then a minus, and then a plus, on and on and on, until you get to, so in my sum now, it's going to be -1 to the m-1 times the one before, because I have minus signs. I have plus signs if the number downstairs is even. Yeah, number downstairs is even, I want a plus sign. There's this fact that if you then add in the very last term, then you get exactly 0. Do people know this fact? Maybe not. I'll prove this fact in a moment. Hello, The Sopranos Reloaded. Welcome to chat. This is Chill Maths, where we just do maths problems quite slowly. This one's taken us more than a week. Not continuously. Yeah, so it cancels symmetrically. That works well if you have an even number of terms. The cancellation just works. So one of my claims on the board here is that 1 minus 3 plus 3 minus 1 is 0. That's the m equals 3 case, which is not very exciting. Maybe a more interesting case is that 1 minus 4 plus 6 minus 4 plus 1 is 0, because that's 8 take away 8. Don't apologise, this is great. It's content. It's helping me think about inclusion exclusion at the moment, which is good. Okay, maybe people don't know why this is true. This fact is true because this sum that I've written down with plus and minus signs is the binomial expansion of 1 minus 1 to the power of m, which is 0. But on the other hand, you could expand this out using the binomial theorem, and you would get this mess. Anyway, so this is kind of a joke, but you could expand this out, and you would get, oh my goodness, so much mess. But actually, weirdly, that's precisely the mess that we've got so far. We've had binomial coefficients for how many choices, how many different ways you might have done overcounting or undercounting, respectively, and they've got plus and minus signs because we've been trying to correct our over and undercounting backwards and forwards so far in the equation, and now it's time for the other sort, I think. I'm concerned that this might be sometimes 0. Give me a second. So what have we got? I'm missing the first term and the last term. I want 1. I want 1. Oh, right, okay. So this says something like, if m is odd, then this first and last term cancel, like in this example, 1 minus 1. If m is odd, then this all cancels. I get 0. So this first term and the last term cancel, and everything in the middle is what I've got so far. So add plus 1. So add this. The next term should have a plus 1 in. If m is even, then this last term and the first one and the last term, are they both 1? So the sum we've got so far is 2. So subtract 1. We've double counted, so subtract 1. Have plus 2, so subtract 1. That's kind of amazing. All of this binomial coefficient stuff, if m is even, then all of this stuff in the middle, the over and under counting and crazy amounts. Yeah, how many ways are there to get 17 long strings? Well, you counted them as adding 4 to this 17 different ways, and then you double counted, I'm afraid. 17 choose 2 different times. Plus minus stuff from the formula so far works out as being 0 or 2. So you either over counted just a little bit, or you undercounted not at all. It was amazing. Good stuff. Rice Cooker Man's here as well. Hello, Rice Cooker Man. Welcome to the stream. Counting problem. Desmos socks. Good distraction, like that. Okay, this has convinced me that it's just plus or minus signs forever. That as you go along, you either see a plus sign or a minus sign, and that my minus dot 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 is not misleading. So that's final answer. There's your number. And if you want it as a probability, divide by 100, choose 12, and it simplifies down to this. There you go, e is better than pi. Thanks for watching, thanks for the problem. Good stuff. The problem is as follows, Rice Cooker Man. Let's go up. Oh, we've got a lot. There we go. You choose 12 distinct integers between 1 and 100 inclusive. They're chosen at random. Find the probability that 4 consecutive integers are chosen. And the final answer is this number here in green. This is not a satisfying answer, but along the way we have come up with different ways of counting these things and making sure that we're not doing any overcounting, or if we are, that we can keep track of how much overcounting we have got. As a decimal, that is 0.011224592885321. It's about 1% of the time, about 1.12%. And now it's time for a cup of tea. There is an animated RFL. I think that the RFL emote comes from. Oh yeah, how do we do that? There's a stream tier reward. I can't remember what anything is called on Twitch. I'm going to make a cup of tea. We never renamed the channel points. Maybe we should think about what that means. Oh, we had some suggested to me because a point is a zero-dimensional object. So we thought maybe we could do something with that, but then I never actioned that in Twitch. There's supposed to be a system where you can unlock extra emotes using channel points, which I thought I'd switched on. Maybe I haven't. Yeah, choose an emote to unlock, 480 channel points. I don't know if that's a lot. It should be on. And unlock a random sub emote, 320. And there's not that many, so what's the probability that you get the sub emote that you want? The sub emotes at the moment are just animated versions of the standard ones because Twitch has automatic. I didn't make the animations. Right, good. Okay, C around E is better than pi. I'm going to make a cup of tea, partly to celebrate our probability number at the end, which I simplified this before the stream because actually working with these large numbers is no fun. Especially because MATLAB is not very good at whole numbers this large. So kind of tricking it to calculate these things and simplify the fraction was a bit of a separate adventure. Rumours that I have 1,000,000 points are a lie. Right. Okay, I'm going to make a cup of tea. I'll be back in a couple of minutes. I'm going to play an ad break. As a reminder, if you see an advert, it is very slowly, incrementally supporting charity, because even when this Twitch channel cashes out, it's going to charity. In fact, that's already happened, but not the cashing out. The charity donations already happened. It's a future. It's a time reversal thing. Don't worry about it. It's just time going forwards and backwards at the same time. It's all right. Right. Enjoy your adverts, if that's possible to do. I'll see you in about a minute and a half. Back. Oh, look at that. Okay. I'm back. Sorry. Maths222 has been sold as CPU. Murray has. Well, Mary Toffee's making a cup of tea. That's where it was. Making this cup of tea. Thanks for the redeem. Oh, wait, no. Who redeems this? It was a Maths222 redemption. Can I mark it as done? No. Okay, right. Goodness me. Right. That was Maths222's turn. Right, a quick reminder, it applies to everyone. You only get to see my cup of tea, but other people are welcome to go make a cup of tea as well. Trying to think about what to do next. We've kind of succeeded at this problem, I think. We can do this now, I think, for any value of 100, any value of 12, and I think any value of 4. Any value of 4? Because, well, you know, there's a 4 here and here. This is about how many things you don't choose, which is nothing to do with the length of sequence you're looking for. Then this 8 is clearly like twice 4. the 12 is 3 times 4, and so on. So I think if you're looking for a sequence of a different length, just change the 4s to 8s or 12s or something. No, change the 4s to whatever number you're looking for. Multiples of 4, change those to multiples of 12 or whatever you need. Right, and then that works nicely, because if you're looking for a string of length 12, you'll start with this term. No, you won't. You'll start with this term with a 1 on it instead, because you start with 1. Okay, right. Yeah, that's the difference. Looking for a string of length 12 is different from looking for 12 things that are in strings of 4 or more, because the second one takes way longer to say. Okay, we've got some viewers and some maths. That is what we do. I could talk about a step. I think I've still got a steps problem in here. I don't know if that was a kind of joke suggestion. I think we've done this one though, haven't we? There's a polynomial question. I do like polynomials. I've got a step stream on the ready in case we need to. Ooh, I might be getting nerd sniped by this. Ooh, factorising polynomials. Ooh. And we maybe don't talk about step. Didn't ban it. We banned the word viewers. In chat. That's a clever way to ban people offering us viewers. I think I'm getting nerd sniped by this question. Okay, we'll have a quick look at this. My other plan is possibly even less good for TV, which is that there's something, if you remember a few weeks ago, nobody remembers this, we came up against definition of like uniform convergence for functions, which is like not the first thing you learn about when you learn about convergence, but it's one of the first things, and I should definitely know it. Something I do on this stream sometimes is take maths topics I can't quite remember that I feel like I should know or I should remember, and I try to relearn them. It doesn't make great TV because, yeah, we did some ODE stuff, and then I realised that I couldn't remember the technical enough to understand. There was a proof in the differential equations notes that relied on stuff from first year maths that I've completely forgotten. At some point I'm going to go back and learn that, but possibly after I've messed around with the step question a little bit. So the reason we were doing step questions months ago is that I was slightly trying to get ready for a step school where I was helping people with step questions, and I wanted to know if I could still do step questions. And it turns out I can just about still do step questions, but not not questions that are much harder than that. What am I doing? Show that provided this, the polynomial can be written in this form, where alpha and beta are the roots of that, and a and b are constants which should express in terms of alpha and beta. My goodness. So I should just expand this, right? And compare terms, which involves quite a lot of multiplying out. I think it's Weierstrass with an IE. I'm wrong. It's EIE. Both. Okay. I'm gonna see what's going on here. Alpha and beta are roots of the quadratic equation like this. Actually, maybe this seems boring and I should do the next part. No, okay, let's keep it going. Let's see if I can do this. 3 alpha x squared plus 3 alpha squared x. I think there's something here about knowing what you know that the live stream is quite helpful for me to realise that there are many things that I think I know that I don't actually know. I've been thinking about the live stream a bit recently because we're hitting our sort of 1 year anniversary of Twitch. It's a year ago that I did the really stupid thing of live streaming my attempts to learn Galois theory. Oh my goodness, I don't know if anybody who watched any of that is still watching streams because, gosh, we've done a lot of maths since then, haven't we? And there's sort of several different things that we've done since then. that have been, I think, different levels of success. I think Quintet Quest was not one of the most successful things, but that's okay. Not everything has to be a massive success. Sometimes we solve a particular problem, and sometimes we're trying to learn theory together, and the theory learning stuff is really hard. But I think we can do. There's something in there to work out how you learn stuff, as well as how you solve problems. So here I've got 4 unknowns, A, B, alpha, beta. They're all unknowns in this new format of the cubic. And we'd like to check that they solve this quadratic and solve for A and B in terms of alpha and beta. It's weird. I guess I've got this one. I kind of want to plug that one in here. Yeah, because then I'll get A in terms of alpha and beta. And then B in terms of alpha and beta. Can I then put them in here to get something in terms of P and Q? If I know A and B, then I'll get something about, well, maybe it'll just magically turn into the sum of the roots is Q over P or something. Oh yeah, I should think like that, right? This is to do with the sum of the roots being Q over P. If the roots are alpha and beta, then to get this quadratic, I can just think about what the sum of the roots is and what the product of the roots is, which is not too bad to think about. Like if I square this, then I get something like. Oh, I'm going to go for one. I'm going to bite the bullet and break the symmetry and do 1 minus a beta is equal to p. So if I square it, then I get a squared alpha squared, sure, and I get this kind of cross term. Maybe I should solve for a first. Yeah, maybe I should solve for a first. This is looking awful. I was hoping this would just tell me something about alpha beta in terms of p squared, because I strongly suspect that the product of the roots is just p. Yeah. Oh, I haven't changed the logo to StepStream. Woo! That didn't quite work. There we go. StepStream. Okay, solve for A and B first. That didn't look good, so I'm going to solve for A and B first. So take these 2 equations and solve for A and B. I'm running out of space over here. I'm going to do my white rectangle trick. Chill maths. White rectangle, good. Okay. Solve for A and B in terms of alpha and beta first. So B is 1 minus A alpha squared plus beta squared minus A beta squared is 0. So A is, oh, I used to be much faster at this sort of thing. Beta squared divided by beta squared minus alpha squared. And similarly, B is, oh, could it please be something nice? Beta squared minus alpha squared minus beta squared over beta squared minus alpha squared. That's not too bad. Right, so that the sum is 1. Whereas A times alpha, is that true? A times alpha, check it back again. Alpha squared times A plus beta squared times B would be, yeah, would cancel out and give you 0. So that's those 2 equations dealt with to eliminate A and B in terms of, in preference of alphas and betas. Okay, now I think I'm going to plug it in. This looks horrible and symmetry breaking and stuff. You know, it's ugly. So now I'm going to plug it in to try and hopefully this turns into P equals, and there's alpha beta. It's the product of the roots. If not, I'm going to have to think. So this is going to be like alpha beta squared. Multiply this first one by alpha, and there's a B term times beta. Oh yeah, okay, I can see how this is going. There's a common term of alpha beta. Hasn't quite done the thing that I wanted, really. There's a common term of alpha beta, and then I've got something else to deal with, which is that I have beta minus alpha upstairs, and I have beta squared minus alpha squared downstairs. What was I hoping for? The product of the roots would be, just be P. And that's not quite happened because I've got this term. I can simplify that, difference of two squares. Do I get the sum of the roots? And I strongly suspect that the sum of the roots is q over p. From reading the answer. I should stop reading the answer maybe and just do the question. But if the sum of the roots is q over p, then I'm looking at the product being q rather than p, which would be annoying. Have I mixed up p's and q's somewhere else then? Not that I can see. Interesting. Plow on, I think, see what happens. Let's rearrange the second equation. This one with alpha cubed in it. Let's see what that says in terms of alphas and betas. Yeah, that definitely says sum divided by the product is p. Product divided by the sum is p. And I want... Something's not right. We'll fix it in a second. Maybe it's my a's and b's. Could it be my a's and b's? Been reading off this line with the alpha squareds in it. From squaring this term, everything's times a alpha squared, b beta squared. I did this while talking out loud. Common cause of problems. Yep, I messed up there, didn't I? I messed up there. This is not an x squared term, this is an x term. So this thing is p rather than this thing. This thing is 0. Forget all of that. Good. Good, good, good. So that means I should be multiplying by alpha squared and beta squared instead. Here's the fix. The p is actually here from the coefficient of x rather than x squared. So the squareds here and here. Now that looks like 0. Bother. Because I should only have alphas and betas. I should fix the other thing as well. Fix this equation as well. The one that was 0 was actually the one with just alphas and betas in. So remove all the squares. Whoops. Small mistake, loads of 2's in the wrong place. We can fix it. Because if you remove all those 2's, then you get alpha squared times the first one. You get beta squared times the second one. And then this perfectly works out to be alpha beta. Maybe with a minus sign. Maybe with a minus sign. I don't really want a minus sign, but maybe with a minus sign. Product. Yeah, close enough. Yeah, the chances that I've got the minus signs correct so far are pretty slim. Maybe with a minus sign for the product. And then the other one's going to give me exactly the sum, isn't it? So Q, I think, is a times alpha cubed. So I should write out this term. And B times beta cubed, which gives me this minus alpha, lovely like this. Which is then, I get an alpha beta at the front, and I have alpha squared minus beta squared divided by beta minus alpha, which is the difference of two squares, and just gives me alpha plus beta with a minus sign at the front as well. So I really think I've missed a minus sign somewhere because I now have that Q over P is the sum. Oh, that would be good for this product in here. Close enough. Minus sign for A? Yeah, it could be. Up here. I'll try to move this thing onto the right. Alpha minus beta. That does unlikely. So I'm trying to solve this. A times alpha plus beta times 1 minus A. And then I think I do get beta. I'm moving the A terms on the right. Yeah, sorry. Yeah. Am I just wrong about how minus signs work in quadratics? Am I wrong about how this minus sign works up here? Did I miss a minus sign up here the first time? Oh, that's very likely, isn't it? That's very likely. Yep, I missed a minus sign in here because these terms have got a plus sign on and it's got a minus sign in the equation. So it was minus p in here, which means it was minus p here. The product is p, but then it follows through. This is minus p. For alpha plus beta, it's minus q over p for the sum or something. No, that minus alpha beta is still... Oh, who cares? We're close enough. We're now close enough. Minus the sum is q over p or something. Got our quadratic. Got a and b. What do we actually do with this question? The reason I like step questions is that you do some algebra like that. It's not really exciting. But then maybe you get to do something. Like, excuse me, solving a cubic. Here's a cubic. X cubed minus 24x plus 48. I wonder what we've done in terms of solving cubics. I'm talking about Galois theory out loud. I should maybe think about that, right? I don't know if I can. I really did not learn Galois theory very well. So maybe I'm imagining here P is 8, Q is 48. If that's the case, then, well, we'd be thinking a little bit about solving t squared minus 6t plus 8. I'm trying to divide it by 8 live. Why would I do that? Why would I divide it live? 8. I just saw myself make this horrible mistake of mixing up two terms. Why would I try and solve it live? Anyway, there we go. Seem to have done that. So 4 and 2. So you can use the previous part to rewrite it. I think I want the values of a and b as well. I don't know how this is going to give me solutions. Maybe these terms are going to be very similar. I don't really see it. Well, let's work out a and b. So a and b, so alpha and beta are 4 and 2. The difference is 2. A is, does it matter which way around they are? Yeah, okay, so if I say alpha is 2, beta is 4, then A turns out to be 4 over 2, which is 2, and B turns out to be negative 2 over 2, which is negative 1. Alpha over the difference. Alpha over the difference is 2. Okay, so I have the expression to solve. After using all that algebra from the first part, I get to write this in the form minus 1 times x minus 4 cubed. Is that good? Well, sort of, because now I can solve that, right? Now I can solve this equation by rearranging and taking cube roots. Huh, that is sort of good. I think we've solved the reduced cubic. I think that is what we're doing. I think that's what we're doing. We've got this cubic, which is very general, because you can translate cubics to make them look like this. And then write 3p and q here for the coefficients. Rewrite them in this form, and then that's equal to 0. Oh, so then you take your cube roots. So if this is 0, rearrange, and you'll get cube root 2 x minus 2 is equal to x minus 4. And then shuffle it around a bit, and I bet you get this value of x. And there might be some factors of omega here, because cube roots with complex numbers. You requested complex numbers, here they are. I is 0, 1, 2 or something. Maybe I should use a different letter, k. If you have two things whose cubes agree, then it might be the case that the numbers are the same, or it might be the case that their ratio is one of the other cube roots of unity. So that's fun. The cube roots of unity are these things that cube to 1. If you've seen e to the I pi as minus 1, you've met one of the expressions for the kind of second roots of unity, I suppose. 2 pi I over 2. 2 pi I over 3 gives you this cube root of unity. Something that cubes to e to the 2 pi I. Also, omega squared would do that. E to the 4 pi I over 3. When you cube it, you get e to the 4 pi I. In the Argand diagram, these lie on the corners of a regular polygon. They're really good. Yeah. Probably they'd like to use the shortcut that everything in school is a real number, except for the unit on complex numbers, and that is quite a good shortcut. It's quite a good shortcut. Because then you get to talk about how that has one solution. And for some people, that's enough maths. Right. is this last case just to think about whether this is worth doing? Is this going to be the same thing? R to the 6. No, this one's going to agree. It's going to match up. This is the problematic case, apparently. I haven't quite seen why, but I haven't quite got... Oh, so if this thing's got a repeated root, maybe that's a problem? Yeah, maybe that's a problem. If it turns out that q squared minus 4p cubed, yep, if the quadratic's got repeated roots, then you don't get two solutions. So beta minus alpha would be 0, so these fractions don't work out. In this special case though, which is where q squared minus 4p cubed is like this, then I guess they are allowed to write p as r squared. P is non-negative. So I'm just going to think about this rider at the end. I wonder if we can just spot solutions to this. Of course we can. Yeah, of course we can. I can spot a solution to this. So this rider at the end, a little bit of question at the end of this step question says, what if you have this where P is this and Q is that? So I plug them in and then look at it. And the important step there is perhaps plugging it in without knowing what I'm going to see. I can't think 2 steps ahead. I have to write it down and then look at it and go, oh yeah, I'm going to try plugging in x equals r. Because that will give me r cubed minus 3r cubed plus 2 more r cubes. Gets me back to 0. Hooray! So I found one root. Let's find the others. I'm just writing it down and then seeing what happens. It's maybe the most powerful trick I know, is to just take one step and see what happens next. Yeah, we're doing a little step stream. I don't know if it's going to last more than the next 20 seconds, because now I want to just quadratic formula that. Go. Write down your solutions. Off you go. R squared minus 4. Oh, they're quite nice, maybe. Yeah, I should maybe think, because b squared minus 4ac is 9r squared, 3r plus or minus. So what is it then? 2r and r? Yeah, okay. Repeated root. Okay. So maybe it makes sense this is the case with the repeated root, but yeah, and we've translated so the sum of the roots is 0, so if you have a repeated root, then the other one has to be negative twice that repeated root. So this is the kind of special case where you get a repeated root. Fair enough. Okay. As I say, not sure it's going to last more than 10 seconds. R works again. Well done. I should have checked plugging things in. I just went straight for the quadratic formula and then thought about factorising. Repeated roots were on the table because there were repeated roots to this quadratic. So we could maybe have been thinking about them. Okay, not a bad step question. Makes us question 3 on paper 3, I think, 2011, whatever. Good. Okay, that was the step stream. It sometimes happens in the middle of a stream that we do a step question. Yeah, I never told you the known viewers number. Who have I met? I figure I've met lots of people. Oh, hello, Vogel Stream. Missed you in chat there. Hello. How's it going? Yeah, how's Maths 222 got away with that? I think the slash has saved them. I think the fact that there's no space before the word viewers has confused the moderator. I think. Yeah, I definitely met. Let's not out people I've met. Yeah. People get these kind of chance to be anonymous, right? Where you. Maybe we met on an open day or something, but I don't need to know that. Okay, totally different persona. Also, I'm using a totally different persona, right? If I'm at work, I'm using my work persona. If I'm on stream, this is a totally different person. Interested in totally different sorts of maths. Right, I am going to switch, I think. No, they've worked out how to get around the moderator. They're going to keep trying until they accidentally get timed out. And we won't even know you've got... Oh, I don't know. It'll be bad. It'll be bad. I think, sorry everyone, I think my plan is to just learn some analysis now, which is not going to be great TV. If you want to call it a day, then go for that. Beware, I'm going to be trying to learn maths. The thing I said wouldn't go well earlier. How do I do this then? I'm going to share this. Share this. We're switching device as well to the learning device. Ooh. Connect. Accept. Pop. Ah, lovely. It's in colour. So I found these notes. These are last year's lecture notes for Oxford. And look, they're colour coded. Isn't this cute? That teaches us about uniform continuity. These are Paul Ballister's lecture notes. If you want a copy, they are on the Oxford Maths website. Let me quickly find a link. I should have found this first. I should have kept the link from when I prepped this. This is, we're going into analysis 2. There is a good chance that, what I'll learn is that I need to go back to analysis 1. Learning is good TV. Harry Potter. Terrible. Right, here we go. And I'm apologising because look, it even says in the lecture notes, unashamedly technical. So I switched to my thing that lets me write on PDFs. If you want a copy of the lecture notes to play along at home, I'm on page 36 of the document, which I think is roughly, 39 of the actual PDF. If you'd like to play along at home. So this is about continuous functions. The payoff will be theorems that are important, which I think includes the one that I cared about a few weeks ago for differential equations. Look at the quantifiers. Here we are. So being a continuous function means that for all points in your set E, I'm going to have to remember that E is the name of the domain of our function. For all points in our domain, and for all epsilon, there exists a delta. That thing that you say so much. For all epsilon, there exists a delta, such that wherever you are, what is this? Is this what I think it is? This is what I think it is. Such that whenever you're close enough, the value of the function is pretty similar to the value at P. So wherever you are, let's draw a little diagram so I can remember what the letters are more than anything else. You've got a domain E, and you've got your function which takes some values, and there's some special point P where you can choose anything you like, I suppose, but for all P in E, you choose your point, and then you also choose a kind of tolerance, epsilon. How close would you like to see the values? I'd like to see them very close, please. So this is f of P. You choose a tolerance, plus or minus epsilon. And around there, you can choose some delta nearby, plus or minus delta nearby, such that the values stay within that tolerance, such that the difference between f of x and f of p for x some point nearby is less than epsilon. And it's in this order so that whatever tolerance you choose, so long as you then get close enough to the point, you can do that. You can't see that half of the screen. Of course you can't, sorry. I see that way too much. The aspect ratio of that bit of the screen is not the same as the physical device in front of me. There we go. We got the point, we got the bounds. You can see the epsilon's here, delta's around here. Okay, close to the point. Uniformly continuous says that you have to do everything at once, everywhere at once. The enemy chooses epsilon is a thing that people say sometimes. The enemy chooses epsilon, a specification for how close your values must be to f of p. I want your values to be this close, says your enemy. And then to satisfy that, you have to find some value of delta such that you actually stay within that range, very close to the value of f of p. Uniformly continuous says you have to do that such that they choose epsilon and you get to choose delta, but it has to work for all p in the range at the same time. If you like, that's the relationship between delta being a function of epsilon the smaller the value of epsilon they pick, well, I guess you should probably pick a smaller value of delta if they make epsilon smaller. But now, crucially, this function delta of epsilon doesn't depend on p anymore. Yeah, so open set continuity is pretty much the same thing, right? Except instead of saying distance less than epsilon, you say something like f of x is in the ball of size epsilon, or do you say no? It's in. Yeah, you need a metric. Yeah, you say it's in the ball of size epsilon around. Slightly different notation, right? That generalizes nicely. Anyway, the mug is the Cambridge mug. It's from a very old Steps summer school. Step Stream mug. On this side, well, it's quite dirty on this side. On this side, it says University of Cambridge, Cambridge Admissions Office. So the joke is that I work for the Oxford Admissions Office, but Stream persona has the Cambridge mug. It's all carefully thought out, right? There's the version of me that goes to work and the version of me that streams on Twitch, and they're totally different people. It's important to have this separation. People ask which is better, Oxford or Cambridge, and I have to remember very carefully which persona I'm in. You know, which one's which. What are we doing? We're learning about this. A bit different. Yeah, I'll take that. Order of the quantifiers. Swapping the for all symbol doesn't affect the meaning. The order of the for all and the sign. So I've normally seen it. What have I normally seen? Continuity. I've normally seen it. Yeah, in that order. Yeah. I think this threw me because I wasn't expecting P and E, but good. Yep. Read the expression left to right. Yep. Delta works universally. Good. Yeah. Good. Okay, so time to look at some weird functions like this example, sine 1 over x. That's the one that's very wiggly near 0, and not defined at 0. Our domain E is just this range here. Round bracket here means not including this left limit. Square bracket means including that limit. It's a way to write down the intervals, with, instead of writing down inequality signs and being very careful to write down these, you can use a different notation where you write down round brackets and square brackets, which is something to get used to, I suppose, that square brackets mean including that limit, that end point, and round brackets mean not. This is a notation that is only really used for subsets of the real number line, but whatever. Okay, there's the thing I remember. Certainly f is continuous in E, and fails to be uniformly continuous. And it's going to be because there's something near 0 where there's no delta that works. Now I'm going to take these very particularly chosen sequences. I never really know how people think of these. I think there's a bit of working backwards in these if you're trying to answer this as an exam question or something. I don't think you start by writing down these expressions. What are these though? These look a bit like, so the 1 over comes from plugging things into sine, and then these values are chosen so that so that we know the values we're going to get. Pi over 2 and 3 pi over 2 are where sine is 1 and minus 1. So these are going to be changing value from 1 to minus 1. It's very wiggly. It switches between 1 and minus 1. Okay. Well, I suppose this you could write out something like this early on as thinking, well, the problem with this function is that it changes value from 1 to minus 1 very quickly. It's very nearby to the 1, you have points where it's taking the value minus 1. So you have this big change in values between these two. Yeah, okay. Let's try and translate this a little bit. For any delta greater than 0, there are ones that are really close together because these points are getting very, very close together because of the 1 over. And these things both going to 0. But the difference in the functions is not less than 1 because it's 2. That shows they're not uniformly continuous because after a while you'll get points that are very, very close together, closer together than delta. but with large difference in value, which is the kind of the key thing to show that something's not continuous, is to find things that are close together with a big difference in value. Here the idea is to get really close to 0. Okay. It is continuous though, which is a bit weird, right? It's continuous because at any particular point, if you have to choose the point first, then near that point, there's just like a well-defined derivative on the function. It's just really quite well behaved. So nearby any particular point, the value doesn't change much. Near some range delta, near to that point. So if you wanted it only changed by 0.1, you can find some tiny range near each point. The problem is that those ranges have to get really small as you move towards 0, because the function is getting very steep over there. I'm saying steep and differentiable, which is not really necessary. These functions don't have to be differentiable to be counterexamples, but still. Okay, trying to think it through without, trying to develop the intuition really, which is the thing I think I don't have. What's this? Cos x squared. So this is just bad because it goes faster and faster if x gets large. So we should think about places where cos x squared bounces between 1 and -1 very quickly, using the stuff we were just thinking about. Cos x squared bounces between 1 and -1 faster and faster. Where's it 1? Where's it -1? These points are where it's 1 and -1. The difference is... those differences are... Oh gosh, what are they calculating here? These differences are going to 0. Do I believe that? Do I believe that? Oh, yes, I do. It's fine. I thought the coefficient in front of n was different, but it's the same. It's 2n pi in both of them. So look, they look pretty similar, really. Okay. There's all these sorts of maths where I do something stupid, like doing a binomial expansion or something, to compare these two expressions. But they're doing something really clever, which is to write the difference of two squares, because they've got square roots in. So think about difference of two squares divided by xn plus yn, and then deal with the fact that you've got xn plus yn, and think about how that's going to infinity. Let's do something really clever like this, and we'll discover the number pi, which is exciting. Whereas I would do something daft, like something really high-powered, like a Taylor expansion, which I shouldn't be doing because this is supposed to be a very basic Spartan kind of course where you only use what you've proved so far. Right. It's very tricky when you start a maths degree, actually, to work out what you're allowed to use in your proofs. It's whatever you've seen in the course so far when you start off. Yes. Will be used in analysis 3. Revenge of the analysis. Always integrating. Yeah, cool. Okay. Okay, so this is good. These properties are the same thing on a closed bounded interval, which, oh gosh, I would like them to be the same thing. So let's carry on. Then I can stop worrying about it, right? So on a closed bounded interval, we're fine. And that's going to be because if you're continuous, now there's going to be something like suppose there were a sequence of points where, suppose there were a sequence of points where for each delta you escaped that by having a sequence of points where the difference, so maybe on 2 points, 2 sequences or something. It's going to be something like there would be 2 sequences of points. This is what you need, the xn and the pn above. 2 sequences of points, or the xn and yn, 2 sequences of points where the difference goes to 0, but the difference between the values doesn't as you look through those different points for different values of delta. Yeah. But that sequence has a convergent subsequence or something like that. So you're then finding a point, they converge to a point in your set because it's complete or compact or whatever I mean. It's going to be something like that on the next page. Subsequence converges to a point. Look at that point. You weren't continuous after all. Let's find out what words I'm supposed to say on page 30. 7 or maybe 40, depending on how you're counting. Right, okay, so Cylon greater than 0 such that for any delta than 0, we'll choose delta as 1 over n, make a pair of sequences. Hooray, that's what I thought. Such that the points are getting really close together, but the values are always large. Since each xn is in here, the sequence is bounded by the Boltzmann-Weierstrass theorem. There's a subsequence. This Sn is some of the subscripts, which converges to some point. Now P is a limit point of AB. Oh gosh, don't remember that, but never mind. This is the magic word I was supposed to say. I was supposed to say Boltzmann-Weierstrass, and I was supposed to say limit point. Oh gosh, what's going on here? The y's tend to the same place. Good. Because the difference between them is tending to 0. So if one of the sequences is a convergent, the other sequence is also a convergent. We're talking about subsequences, sorry. Oh yeah, because we've got 2 sequences. So you take a convergent subsequence of one of them. You have the kind of break symmetry here. I've seen proofs like this before, I think, and it is annoying that, yeah, you have 2 sequences at the x ends and the y ends, and then you want to use Boltzmann-Weierstrass, so you sort of pick one of them. You pick the x sequence, you talk about the convergent subsequence of that one, and then you check that, the other sequence, because of the properties. So you've got the other sequence also converging to the same point, right? Feels like your break symmetry, right? There's an x here, no y in that sentence. There's a y here, no x, never mind. It's fine. By continuity P, algebra of limits, continuity P we have, and now they're going to tell me that the values on the subsequence. Right, okay. There's a triangle inequality here. What's going on? What's going on? Oh, right, okay. So continuity says you've got these 2 sequences of points that are going in towards P. They're getting very close to each other. They're both going towards some limit point P. Look at the function values on those points. We thought they were all bigger than epsilon, but actually they're going to 0 because of continuity. Contradiction. That contradiction came at a weird angle for me. I don't know. I think I was expecting the contrapositive or something. Anyway, never mind. Yeah, if you're playing along in R to the n, then you've used some sort of Heine-Borel fact. Good. Okay. Global property. Okay. These are the ones both closed and bounded are required. Show that closed and bounded. The first one wasn't closed, the second one wasn't bounded. F itself being bounded did not help at all when it came to uniform continuity. Yeah, fine, yeah, okay. That both functions were bounded between -1 and 1. Mod f less than 2. Okay. Good stuff. I like it. Okay, so that's uniform continuity. There's a definition of a Lipschitz continuous, which I think we saw on the DE stream, so I feel more happy about this. Bounded derivative in place Lipschitz, we talked about this a couple of weeks ago, so I'm going to skip this a little bit. This has got kind of unbounded derivative, so you can do stuff like this to find points where the difference is very large. Are we going to prove that these are blah 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 blah? Are we going to prove that these are uniformly continuous? Proving the following is question 3 on problem sheet 4. If f is continuous, then f is unicontinuous if and only if, as you get in towards this danger point on the left. If you have a danger point, then check if the limit as you're going exists. I guess then you can put that point in and get a continuous function on the left, so that's fine. So then you're good. You're now continuous on a closed bounded thing. If not, the other way around, you're going to have a uniformly continuous function and need to show that that limit exists, which is fun. Something like get close to it and use the uniform continuous epsilons and deltas to show that it's not changing very much as you get close. Yeah, something like that. Piece it together. We've got to the definition of uniform convergence, I think. So I'm going to read it, but we're getting close to 4 o'clock, so I might be calling it a day. So, yeah, I shouldn't have invited this question really. I had to think really hard. I really enjoyed studying at Cambridge. I think it was really fun. On the other hand, we had Saturday lectures, and I think they're still doing Saturday lectures, which is not everybody's cup of tea. But look, I'm doing maths on a Sunday as well, so I think it's fair to say that Cambridge is my cup of tea. Excellent. Right. Okay, different limiting processes. Yes, good. Okay. Pointwise convergence. Yep. Pointwise, if they move inwards, from silent and such that these functions are getting close. And there's for all x outside here a kind of global thing, such that, yeah, okay, does it for all x at the same time, right? Is that what's going on? Yeah. Converge pointwise. For all x there exists. Oh, the problem is that continuity doesn't go across this limit. But maybe if we're uniformly continuous, then it's okay. Can't remember. Let's find out. Or time on the clock. Partial sums converge pointwise. So for all x, if you wait, no, it's not global because it's not global because the for all x is on the outside. That's wrong. The thing I said. Because this says for all x, you can then go and choose n afterwards. So you might have to wait a long time for any particular value of x before this starts to look like the limiting function. F infinity kind of thing. You might have to wait a long time. Yeah, it might matter. For example, these ones take a really long time. Is that true? Maybe, maybe not. With steeper lines coming in, so this gradient is steeper and it comes down to 0, which is why you put in what I've read. You get 0, good. So these steeper and steeper lines as n increases. There we go. Pointwise limit is not continuous. The limit, oh look at this, here we go. Iterated limits may squabble. They must be handled with care, and there's an exclamation mark on the screen in the notes, which is nice. Limit as x goes to 0, limit n tends to infinity of f(n) of x is the limit of x tends to 0 of this limiting function thing, pointwise limit, which is 0, but if you take the limit as you go into x first of fn, well, they were all 1 up here on the left, and they give you the limit as n goes to infinity of just function 1, you get 1. So these limits, you can't swap the order of the limits, which is irritating in a way. The kind of thing that the pointwise limit function is not continuous. And as you come in towards 0, you get these zeros on this. They're squabbling, yeah, it's giving them a bit of character, I guess. Uniform continuity leads to stronger results than continuity 1 point at a time. The idea in the definition of uniform continuity was to require a universal delta. Parallel definition. I'm going to read the definition even though we've hit 4 o'clock. Sequence of functions. Fn converges uniformly if, hang on, what's down here? The order of the for all and for all x does not matter. This one was slightly more convenient, fair enough. You can choose an n kind of globally for all values of x that just works everywhere, which we couldn't do before with those steep line functions, because some of them, even if you make n large, some of them are still up at 0.75, 0.8 or something at some values of x, close to 0. Okay, so you want to make this get close to the limiting function f everywhere. You might have to wait for it, but if you wait long enough, it'll be close to that function everywhere, which our previous things weren't doing. Some of them were hanging around near 1. Actually, all of them were hanging around near 1 for some x. They were all in on it, no matter the steepness. Anyway, this holds we right. Fn tends uniformly to f with a little u up here, specifying that E is integral part. Oh, okay. Where's E? Here it is. Order of quantifiers matter, independent of x. Probably will depend on epsilon immediately from the definitions. If this, then it converges pointwise, that's all fine. You choose your value of n to just be the one that works for all values of x, if you're given a particular value of x. Good thing, capital G, capital T. Oh, these notes are fun. I like these. I like the morals and the squabbling. This is a good page. I can't remember what the ML bound is. Was that? No, I really can't remember. So uniform limits preserve continuity, but maybe not uniform continuity. Yeah, that sounds like the sort of fact that I might have been told before. We'll find out, I think. Right, and this proof is not long, so I am going to look at it. Fix some point and epsilon. Good, because you have to do it everywhere. For all values of epsilon, I think, right? For all values of epsilon, you have to do it for all points. By uniform convergence, find an n such that this thing is less than very small. For all x. A uniform convergence, you can do this such that for all x inside here, once n is larger than big N. And then if you've got some number small n that's large enough, then near to that point, the function doesn't change very much. Now choose delta by the continuity of fn. Oh my goodness. And delta exists because fn is continuous along the way. Now choose fn. Delta depends on n. But, okay, now we fixed n, I suppose. So for this particular value of n, you can look close enough to see that the values are less than this. I don't like the way delta depends on small n. So this adds up. And the 3s are because we're adding 3 things together or something. Distance because you are looking at one of the functions in the sequence rather than the limit, and you're looking at a different point. And what's this term for? Oh my goodness. Oh, and then looking back to see what the value was back again. Oh look, 3, there are 1, 2, 3. The differences in values as you move around like that. Oh, so the n ends up not mattering so long as such an n exists. You can jump around on it using its continuity property. That's very clever. Handle that first term. What, this one? Yeah, simultaneously for every relevant x. Every x in E. Huh. Ooh, and it's slightly stronger because it does it for each point P. You can just look at some of the points P, but this is a sidetrack sort of thing, I think. Good, right, okay, we're going to stop there. I can't remember the large loopy ML bound things. Oh gosh, is that doing an integral around a big semicircle or something? Has that got a name? Okay, cool. Right, Maths 222 is off doing some complex analysis or something. I've skim read a bit of notes, trying to learn what uniform convergence is. Again, I knew it one day, knew it once many years ago. Maybe one day in the future I will be happy with uniform convergence and be able to remember it on the spot. That'd be a good day. Until then, we keep learning. Learning maths is good. Yeah, that's the sort of thing I'd like to be comfortable with. In my life, I sometimes have large semicircle bits of integrals that I would like to say go to 0. It's probably a uniform convergence sort of thing because, gosh, I've probably got a couple of variables in there, one for the function of the values around the semicircle. I think I'm integrating it or something, so maybe it's just a number, who knows. Yeah, I've got a function, I've got an integral, I've got a limit as this thing goes to infinity. There's a double kind of, there's a lot of problems there, right? That sounds like the sort of thing I would like to be able to do. I am wrapping up a bit. How can I help? Before I go, this is cool, isn't it? Oh, bounded by max times length. Oh. I don't remember. Oh, Mary says bye. Bye, everyone. I think I'm calling it there. We got to slightly past 4 o'clock. That is how this thing goes. I need to remember to chop the first 2 minutes off before I'm muting myself. But now I should remember to do the opposite and mute myself. I think I'm back next week. Let's have a look at it. Let's have a look. I should plan this before. I think I'm back next week. Yeah, back next week. Maybe for this, or maybe I'll take this offline, get really good at this, and then tell you what I found out. Maybe with, who knows, different sort of counting problem. Do have a different sort of counting problem. Oh no, get well soon, Neutrino. Yeah, we'll see. Right, okay. Take care, everyone. Bye.